Hello everyone, welcome to the e-learning platform of Himachal Pradesh University. This is Dr. Vijayata Pathania, Assistant Professor in Mathematics, Himachal Pradesh University, Regional Center Dharamshala. Today we will learn about partial differential equations and the main topics we will cover are linear partial differential equations of second order, classification of second order partial differential equations, solution of two-dimensional Laplace equation by using the method of separation of variables, and after that solving the Dirichlet problem for a rectangle under some boundary conditions by using the method of separation of variables. So first of all, what are linear second order partial differential equations? The general linear partial differential equations with one dependent variable u on a domain omega of second order into independent variables x, y which belongs to domain omega is any equation of the form equation number 1, where a, B, C, D, E and F are real constants or may be functions of x and y. Also, equation 1 can be written in the form of equation number 2. Since we are talking about the second order partial differential equation, so we retain the second order partial derivatives as it is and others we club in this form, which is equal to j. The general linear partial differential equation of second order with one independent function u on a set of points x is equal to x1, x2, so on up to xn, where n must be greater than 1, is given by equation number 3. The main difference between equation number 1 and equation number 3 is that here we have considered the two independent variables x and y, but in equation number 3 we have considered the n independent variables x1, x2 and so on up to xn. Now the classification of second order partial differential equation. Consider the linear partial differential equation of second order in two independent variables x and y which belongs to domain omega is given by again equation number 4. Now this equation number 4 is elliptic, parabolic or hyperbolic at any point x0, y0 belongs to omega according to the discriminant b square minus 4ac is negative, 0 or positive, as if the value of b square minus 4ac is less than 0, then the given partial differential equation is elliptic partial differential equation, and if the value of b square minus 4ac is equal to 0, then the given partial differential equation is parabolic partial differential equation. And in the same way, if the value of discriminant b square minus 4ac is greater than 0, then the given partial differential equation is hyperbolic partial differential equation. So here are the examples of elliptic partial differential equation, parabolic partial differential equation and hyperbolic partial differential equation. The best example of elliptic partial differential equation is the two-dimensional Laplace equation, which is given by equation number 5. So if we compare this equation with equation number 4, we have the value of a is equal to 1, the value of b equal to 0 and the value of c is equal to 1. So if we substitute these values in the discriminant b square minus 4ac, then we have the value of b is 0 minus 4, the value of a is 1 c is 1. So its value is minus 4, which is less than 0. So this Laplace equation is the elliptic partial differential equation. Now next is the parabolic partial differential equation. The best example of parabolic partial differential equation is the one-dimensional heat conduction equation. And in this case, if we compare this equation number 6 with equation number 4, we find that the value of capital A is equal to c square, the value of B is 0, and the value of C is again equal to 0. So the value of discriminant B square minus 4AC is equal to 0 minus 4 into C square, and the value of C is again equal to 0. So 0 minus 0, which is equal to 0. So this is the example of the parabolic partial differential equation. And similarly, the best example of hyperbolic partial differential equation is the one-dimensional wave equation. If we compare this equation number 7 with equation number 4, we find that the value of A is equal to c square, the value of B is equal to 0, and the value of C is equal to minus 1. So if we substitute these values again in the discriminant b square minus 4ac, we find that b is equal to 0, minus 4, the value of a is c square, the value of c is minus 1. So minus minus plus, which is equal to 4c square, and this is greater than 0. So the one-dimensional wave equation is the example of hyperbolic partial differential equation. Now we come to the solution of two-dimensional Laplace equation by using the method of separation of variables. We know the two-dimensional Laplace equation in Cartesian coordinates is given by equation number 8. We assume the solution of equation 8 in the form of equation number 9, where x is the function of x only and y is the function of y only. So after that, partially differentiating this equation number 9 twice with respect to x and y respectively, we have equations in the form of 10. So substituting these equations 10 in equation 8, we can obtain this equation. So after that, dividing throughout by xy, we obtain the result in the form of equation number 11. And equation number 11 holds only when this is equal to some separation constant k. Now, here the value of k will be either positive, negative or 0. So three possibilities arises to obtain the solution. First case, when k is greater than 0. So let us assume the value of k be equal to p square. If p is negative, then again k is positive. Therefore, equation 11 becomes, here we substitute the value of k is equal to p square. K equal to p square. So after solving these equations and rearranging the terms, we have d square minus p square into x is equal to 0 and d square plus p square into y is equal to 0. And its auxiliary equation is given by d square minus p square equal to 0, and the auxiliary equation of this equation is given by d square plus p square is equal to 0. So after solving this equation, we get the real roots as plus minus p, and after solving the second auxiliary equation, we get the imaginary roots as d equal to plus minus iota p, and we know when the roots are real, then its solution is given in this form, and when the roots are imaginary, then its solution is given in this form. So here C1, C2, C3, C4 are arbitrary constant. So its complete solution is given by substituting these values in equation number 9. So the solution for this case when k is greater than 0 is given by equation number A. Case 2, when k is less than 0. When k is less than 0, then we assume the value of k is equal to minus p square. Therefore, substituting this value of k again in equation number 11 and repeating the whole process, we get the auxiliary equations in the form of d square plus p square equal to 0 and d square minus p square equal to 0. So here from the first auxiliary equation we get the imaginary roots, and from the second auxiliary equation we get the real roots. So the solutions of imaginary roots are given in the form of trigonometric function, and if we obtain the real roots, then we obtain the solution in the form of exponential functions. So here again C5, C6, C7, C8 are arbitrary constants. Now substituting these solutions in equation number 9, we get the solution when k is negative in the form of equation number B. So the third case is when k is equal to 0. If k is equal to 0, then equation 11 implies x double dash is equal to 0 and y double dash is equal to 0. Double integrating above equations with respect to x and y, we have its solution in the form of this equation and the solution of the second equation in the form of this equation. So substituting these values again in equation number 9, we obtain the solution in the form of equation C. So here we have solved the Laplace equation and we obtained the three solutions in the form of equation number A, B and C depending upon the values of k as positive, negative and 0. So in the last we will solve the Dirichlet problem for a rectangle, that is Laplace equation under some boundary conditions. Since the Laplace equation is given by curly square upon curly x square of u plus curly square upon curly y square of u equal to 0, where the value of x varying from 0 to a and y varying from 0 to b, and the boundary conditions are given as, the first boundary condition is when x is equal to 0, u is equal to 0. When the value of x is equal to a, u is again equal to 0. And also when the value of y equal to b, u is equal to 0. And when the value of variable y equal to 0, the value of u is f of x. So here we have this type of Dirichlet problem for a rectangle. Suppose this is x-axis, this is y-axis. Here we have x is equal to 0. So the value of u is equal to 0. This is our first boundary condition. And in the second case, when x is equal to a, u is again equal to 0. This is our second boundary condition. And in the third boundary condition, we have given that when the value of y is equal to b, u is equal to 0. And in the fourth boundary condition, we have given when y is equal to 0 on the x-axis, y is equal to 0, the value of function u is equal to f of x. So we have to solve this Laplace equation using this boundary condition. Now in the previous section we have solved the Laplace equation by using the method of separation of variables, and we have obtained the three solutions in the form of equation A, B and C. So out of these three solutions A, B and C, we choose only that solution which is consistent with the physical nature of the problem and the given boundary condition. So first of all, we consider the first solution which is given by equation number A. So in this solution we use the first boundary condition, that is, and our first boundary condition is u of 0 y equal to 0, that is when x is equal to 0 the value of function u is equal to 0. If we substitute x is equal to 0 in equation number A, the value of u is equal to 0. So the right hand side is c1 e raised to power something e raised to power 0 is equal to 1 plus c2 into e raised to power 0 is again equal to 1, and in the left hand side we have 0. So equation A becomes in equation A becomes in the form of equation 12, because 0 is equal to c1 plus c2 into c3 cos py plus c4 sin py, and from here we have c1 plus c2 is equal to 0. Now again, using the second boundary condition, that is u of ay equal to 0, in solution A we have 0 is equal to c1 e raised to power pa. In place of x we substitute a. So we obtain the solution as c1 e raised to power pa plus c2 e raised to power minus pa is equal to 0. Now we have two equations 12 and 13 and two unknown constants c1 and c2. Now to determine the value of constant c1 and c2, we will solve these equations 12 and 13. To get the non-trivial solution, we have the determinant of their coefficients, that is c1, c2 must be equal to 0, and this thing implies the determinant of the coefficients of c1 and c2 is equal to 0. And after simplifying these values, we arrive at the equation 2pa equal to 0, as a can't be equal to 0 and 2 can't be equal to 0, because we have given the range of x varying from 0 to a. So this thing implies the value of p is equal to 0. If p is equal to 0, then solution 13 implies c1 plus c2 is equal to 0, and from here we get the trivial solution, so which is not possible. Now again we consider the solution given by equation C. So solution given by equation C is in the form of equation 14, and here again we use the first boundary condition, that is when x is equal to 0 the value of function u is equal to 0. The above equation becomes u is equal to 0, so our left hand side is 0, x is equal to 0, so the first term becomes 0, and we will have c10 into c11y plus c12 is equal to 0, and this thing implies the value of c10 is equal to 0. Again we use the second boundary condition in equation 14. We have c9a is equal to 0, as a can't be equal to 0, therefore c9 is equal to 0. Since c9 is equal to 0, c10 is equal to 0, so again we get the trivial solution. So the solutions given by equation A and equation C are ruled out. So we have only one solution which is given by equation B, and that solution is u of xy is equal to c5 cos px plus c6 sin px into this term. So using the first boundary condition, that is u of 0y equal to 0, equation 15 implies u is equal to 0, so the left hand side is 0, and here we substitute x is equal to 0, and we know cos 0 is 1, sin 0 is 0. So equation 15 implies c5 into c7 e raised to power py plus c8 e raised to power minus py, and this thing implies the constant c5 must be equal to 0. So we substitute c5 equal to 0 in equation number 15. We have u of xy is equal to c6 sin px into c7 e raised to power py plus c8 e raised to power minus py. And using the second boundary condition in equation 16, we have, and the second boundary condition is when x is equal to a, u is equal to 0. So equation 16 becomes 0 is equal to, in place of x we put a, and this thing implies c6 sin p is equal to 0. As c6 can't be equal to 0, if c6 is equal to 0, then our solution becomes trivial. This thing implies sin p is equal to 0, and we can write this as sin n pi, and after comparing these two terms, the value of p is equal to n pi, where n is the natural number. This thing implies the value of p is equal to n pi upon a. Now substitute this value in solution 16. We have u of xy in this form, and after that rearranging the terms, that is clubbing the constant terms c6 and c7, and we rename it as an, and c6 and c8 as bn, we obtain the solution 17. So in solution 17 we have used the two boundary condition, and after that we use here the third boundary condition, and our third boundary condition is u of xy is equal to 0, that is when y is equal to b, u is again equal to 0. So substituting these values in equation 17, we have the value of constant bn in terms of an in this form, and after that substituting this value in equation 17, we obtain the solution in this form, and after simplifying this equation we obtain this equation in this form, and the constant term is given by this equation. Now using the principle of superposition, we combine all the solution, so we get equation number 18, and in equation number 18 we use the fourth boundary condition, that is when y is equal to 0, u is equal to f of x. So equation 18 implies when y is equal to 0, the value of u is f of x, y is equal to 0, so we have summation n varying from 1 to infinity an into sine hyperbolic n pi b upon a with negative sign into sine n pi x upon a, which is the half range Fourier sine series, and the value of this constant term is given by this integral, and where the value of an is equal to 2 upon a into sine hyperbolic minus n pi b upon a into this integral, and after that we substitute this value In solution 18, we obtained the result as u of xy is equal to this, and which is the required solution of the given Dirichlet problem. Thank you.